This is a lesson on modeling and regression for quadratic functions in a precalculus course. In a previous lesson, I had covered modeling with linear functions, and you can go check out that lesson if you'd like. What I emphasized while I covered this was making sure that you're looking for keywords and phrases in the problem statements that have mathematical implications, using symbols and creating an algebraic equation, right? We're shooting for using our algebra skills. We're not going to be able to solve these numerically. You may be able to solve things just looking at a graph, but you are responsible for solving with algebra. So we need to go for an algebraic equation when we're reading our problems. Use algebra to solve, and then finally make sure that you are showing a graph, that you're checking the graph, that your solution on the graph corresponds to what you did in your algebra. So as we move forward to modeling with quadratic functions, we're going to remember that words mean things. One thing I'm going to add in here that's a little different than modeling with linear functions is this a place in the course where I really see students need to maybe draw a picture to help set up their equations. When you're looking at creating an algebraic equation, that picture can really help organize the information. This is different than a graph. Like if you're working with a box, draw the box. Don't just draw a graph from the equation, but actually draw that box to help you figure out what that algebraic equation is, to relate the symbols in your problem to the givens. So we're going to focus on using algebra to solve, keeping in mind that we have three forms of the quadratic equation that we can work with here. All right, there's the general form, there's the vertex form, and there's also a factored form down here. I don't see the factored form very frequently given in problems for quadratic functions when you're solving word problems, but it may come in handy. Knowing that I can just do x-intercepts in there isn't too bad of a thing. A general form that is very reliable, again, is the general form of the quadratic function here, where I have an a, b, and c. And often I will shoot for that form because I know how to find the vertex from that form. It's kind of easy to solve for intercepts from that form. And so when we're using algebra to solve, sometimes you'll just be given a simple, like, get the equation and evaluate it at a value. Not hard to do. But other instances, you're going to be solving for intercepts, more frequently like crossing the x-axis or the independent variable, right? The input variable, or finding a vertex. So when we're looking at words mean things, we're looking at minimizing, maximizing, the peak, the least number, the key terms, critical terms that indicate a critical value that we would look for on the graph. And finally, again, verify your algebraic solution with a graph. I don't think I can emphasize that enough as many times as I said it. What I've chosen today are a series of problems that I see students struggle with in this material. And the first one is pretty basic here. It's just a rectangle. I have a couple of rectangles here. I'm going to work on the first one and then move on to the second one. And at some point here, I'm going to set up equations, but I might not necessarily solve them. But usually that's why I find students have trouble with is setting up the problems. The algebra skills required to solve, you've developed and we're practicing at this level, but often translating that word problem to an equation or two to be able to solve is the largest barrier. The first problem here, rectangle is drawn so the width is 23 inches longer than the height. So this is where I'm saying draw a picture. So we're going to draw a picture of this rectangle. I'm going to draw a rectangle here, and it says that the width is 23 inches longer than the height. So I'm going to call this H. So it has an H on both sides, and then the width here is going to be the height plus 23. That's how I'm interpreting it there. And there's a width on the top and bottom. If the rectangle's diagonal measurement is 65 inches, find the height. So they're telling me this distance here, the diagonal across here, is 65 inches. They tell me that value. Well, looking at this, I see a right triangle. You may see a right triangle here. We have two of them butted up against one another with that diagonal sharing, right? And I remember Pythagorean theorem, so I can write that down, Pythagorean theorem, all right, which is a squared plus b squared equals c squared for a right triangle here. And what I can see is I have the two sides, right? I have a height squared plus a width squared, and that has to equal 65 squared. Okay, so at this point in precalculus, you're expected to know some geometry, and you're expected to know at least the Pythagorean theorem in this form, right? To know available equations when we're working with shapes. Okay, so it says find the height. Okay, I'm noticing I have two unknowns. I have width and height. When I wrote this equation out here, I have a height squared and a width squared, and that's two variables. What would be ideal is if I got this equation in terms of one variable, and I can. They told me this other relationship. So when I'm talking about writing out equations and relating them together to get an equation of one variable, we're going to have one equation here and a second equation here, so we're good to go, right? For how many ever variables we have, we need that many equations. So 1, 2. I wrote this down and you didn't even think about it. I wrote this down because that's what we're going to need to relate all the information. So what I'm going to do is a little substitution in here. I'm going to put what I know about w in this equation here. So h squared plus h plus 23 squared equals 65 squared. Okay. I would say that if you were less ambitious, if you weren't in a corner, somebody making you do the algebra on this, you could just put that equation into Desmos, and I would put an x here instead of an h, and it would return to you the answer, right? This is parabolic. I have h squared. And so I know the highest power is 2, so it'll be a parabola. What you can do is multiply this out. I think that's another thing you could do here is multiply it out. H squared plus 46h plus 23 squared has to equal 65 squared. All right, that's a perfect square, so I expanded it out into its terms for a perfect square. I'm getting 2h squared plus 46h plus 23 squared minus 65 squared equals 0. We can see that there. All right. And if we simplify this, this is 529. And this is 4225 if you square those things. So if you simplify this, I'm going to divide by a factor 2 on both sides. And when I simplify this, I get this equation. H squared plus 23h plus, this turned out to be negative 3696, and if I divide by that by 2, I get 1848. That equals 0, and so that's another equation that you might put into Desmos, is just see where this function crosses the x-axis. All right, I did both of these things. And you may see these little pictures up here. I think what you can do is you could use a quadratic formula in order to solve. Right? There'd be two solutions technically, but I have a feeling that we only want a positive solution. So you go negative 23 plus or minus the square root of 23 squared, blah, 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 divided by 2 times 1. And that would give you two answers to solve with the algebra. I put the graphs up here that I created. The first graph I'm going to show you here is this one. Let me bring it to the front. Bring to front, and you can see that I set my original equation and I put x in there instead of h like I mentioned. Here's the parabola, the original parabola. The red part is that h squared plus w squared term. And then I said, when is that equal to 65 squared? I didn't even calculate it. I just put 65 squared in there, and you can see the answer, right? And so that comes up on my graph. There's another solution over here that I didn't show. It's the negative solution, but I don't care about the negative solution because this is a rectangle. A triangle and a rectangle. We can't have a negative height for a geometric object. So I'm not interested in what's going on the other side where that negative solution is. So I'm seeing that the height is 33. 33 inches. I do believe when you can factor this. I actually think this factors down here. H plus 33, and then whatever H plus whatever factor 33 multiplies by in order to get 1848, that would be the other answer, and then you would know that was the solutions. And I do believe that's on this other graph I have pulled up here. Let me bring it forward. Bring forward. We can see that there's 33. So when you graph just this equation here, you're asking when does that cross the x-axis, and we can see it's at 33 and negative 56. So like I was saying, I don't care about that negative 56. That's not an answer that I care about. The answer that I care about is 33. And I'm going to note, I just noticed this here, I have a typo with my problem, and that's why I'm not getting the right signs here. So this should be a minus when I subtract those. That's a minus, and then that would make this a negative and this a positive. And then that would make my solution be verified with my graph, right? I have a negative 56 and a positive 33, and that comes out in my solutions there. Okay, the bottom one here is another rectangle. It says the length of a rectangle is 5 inches longer than it is wide. If the area is 84 square inches, what are the dimensions of the rectangle? So I'm going to help you set this one up. It says that there's a length. The length is typically longer than the width. All right, so when I draw this, I'm not going to do a length here and a width here. I'm going to say that the length of the rectangle is 5 inches longer than it is wide. So on my picture, L is the longest side here. L is W plus 5. Okay. So that's setting up my first equation. I think just using that information will help me set up this first equation. The second equation I need to go for is given in the information about this area. If the area of a rectangle I know is length times width, and I'm going to write it that way because it says what is the dimensions of the rectangle? Well, I want this in one variable, right? So if this is equal to 84, right, here's the second equation, here's the first equation. If I do a substitution, if I take this L term that I know and plug it in over here, you all can see that now I have one variable in my equation with that substitution strategy rather than two. I'm going to distribute this W here, 5W. I'm going to subtract 84 on both sides and get a 0, so I'm in the general form for the quadratic. And you can solve using the quadratic formula, or that may factor. I have a feeling that may factor just with those integer values, but that's how you set up that part. Another one in here is the breaking even example. It says the cost formula for a company can be modeled by, so this is a cost. That's how much it costs the company to make the items. X number of items. The formula for the income, the revenue, usually this is R for revenue, they're calling it income, but revenue is this equation. And I'm going to note both of them are quadratic. They're both quadratic equations. It says a company will break even when its cost equals its income. How many items must the company make and then sell to break even? Okay, so we're breaking even, and the key thing that we need to note on this is that when we break even, the cost is going to equal the revenue. All right, so we're just going to set these two things equal to one another. 1540 plus 25x plus 0.2x squared has to equal 104x minus 0.8x squared. Okay, so now we can move ahead and solve. For me, when I look at this, I'm seeing some decimals in here. I'm seeing some really large numbers. My feel is I'm not going to want to factor it. I'm going to use the quadratic formula on it, which means I need to get into the general form of the quadratic equation. So what I'm going to do is move my x squared and move my 104x over to the other side. That'll leave me a 0 on this side. And I'm going to arrange them in least the highest power of x to the smallest power of x. So 0.2 plus 0.8 is a 1x squared. You don't have to put the 1 there, but I wanted to make it explicit for you that it's a 1x squared. We're going to have 104, negative 104 plus 25. Negative 104 plus 25 is negative 79x. And then we're still going to have the 1540 there sitting there. There was no way for it to change. It's just a constant. Okay, so like I said, you could use, in order to break even, we're solving for x. We need to know what x is. I think you could use the quadratic formula on this one. If you weren't sure what to do, the quadratic formula is always going to work. So I would say 79 plus or minus the square root of 79 squared and blah, 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 2 over 1. You keep filling that in. And you're going to find two x's. You're going to have the positive case of this and the negative case of this. And then also, another way to solve this, it turns out you may note when you do the quadratic formula that you get some integers here. Actually, when you do this, you get 44 and 35 when you solve. So I'm going to make note over here that this actually factors into 44, x minus 44 minus x times x minus 35, all right? And that would give you the two solutions too. So this is one way of solving, and this is a second way of solving. There's no real preferred way. I wouldn't have played that game trying to figure out how to factor 1540. I would have used the quadratic formula on this one. However, what you do want to do is, you already may have done this or been wondering what it looks like. You know, I have already pulled up the graph for this thing, all right? So those are the two functions that we're looking at. There's the cost function, is the blue parabola. Oh, I'm lying. No, the cost function is that red. And how do I know? I have a positive coefficient in front of this one, so that's an upward pointing parabola, and you can see that's the red one here, all right? The blue one is downward pointing, and when I look at where those two parabolas intersect one another, that is at 35 and 44. I can see that right in there, 35 and 44. So that verifies my solution that I did with the quadratic formula, and notice that I could factor it too. The next problem I have for you is building a fence for 3 horses. This is a more complicated problem than what I have in the lesson that I put together for you all if you're in my class. But I'm doing the harder example here. Students typically, once you catch on to the harder example, hopefully you can go back and see the trick for the less hard example. Bob wants to fence in a rectangular area of his field using so much fence he has. Apparently he has this much fence. The area will have 3 equal fenced off sections for each of his 3 horses. That's cute. He wants to maximize. Okay, so key term in here, maximize. I'm going to note that right away. When I see maximize in a problem statement, I am going to note that I will have to find the vertex of a parabola. So I need to get a quadratic form that I can easily find the vertex of a parabola from. the area of the field in order to give his horses the most pasture possible while keeping them separate. All right. So here's the picture that was provided in the problem here. You can see that there's a length and there's a width. I'm going to call the length script L and the width W. I like script L because if I just write L, you don't know if it's 1 or whatever. So that's why I write a script L. So when I look at the parts of the fence that are entailed in building this fence, when Bob goes out and builds this fence, he needs 2 links. He needs one on the top, one on the bottom. And then when I look at the widths, he needs a width on each end, but because there's 3, he's going to have 2 more in the middle. There's a width here and a width of fence here. He needs fence along all of these lines. Okay, so when I look at all of that fence added up, he has so much fence, and all of that needs to add up to 1780. Okay, I haven't even read what the problem's doing. I'm just kind of putting together the information from the problem statement. So I'll say 4 W's plus 2 L's has to equal 1780. Okay, so there's, like I said, if I have 2 unknowns, I'm going to have 2 equations, and this is one relationship I'm given in the problem. The other relationship that I'm going to have is the area, which is length times width. We know it has to be length times width. Let's read the problem down here. Define the function length in terms of W. So I have the length as a function of W to represent the length of the field as a function of the width. Well, I wrote down an equation here. If I solve this equation for L, that would give me L as a function of W. Right away, I see I can divide this equation by 2. Divide all of these terms by 2, by 2, by 2. And then I can move this term over to this side. So I get 1780 divided by 2, which is... 890 minus 2W, right? If I divide 4W by 2, I get 2W. So this is my answer to A. This is what A is looking for. You're going to take that perimeter of fence, all of the fence added up, and you're going to make that relationship and then solve for L in terms of W, okay? B asks to find the function area as a function of width. So when I look at B here, I want to take this area and I want it to be a function of width only. Well, luckily, I already know that it's width times length, but I have length in terms of W, so I can take W times L and do the substitution in here, what I know about L, 890 minus 2W. So when I get this function of A as a function of W, I'll get negative 2W squared plus 890W. And I arranged it this way. It's easier for me in a quadratic form, right? AX squared plus BX. We don't have a C in here, but I'd be able to put a C. I always put it in that general form, the familiar general form, so I can identify A, B, and C's easily. All right, so this was my answer for B here. I have the area as a function of width. Now what I can do is say, okay, I have a parabola. Remember earlier I said if I want to maximize the area, I'm going to look for the vertex on the area function. So in order to find that vertex, I'm going to take the maximum width, W max, has to equal negative B over 2A. Remember, to find a vertex, the input value for the vertex, I do negative B over 2A. So I go negative 890 over 2 times negative 2. So I get 890 divided by 4, which is 222.5. And this is going to be feet. Determine the maximum area as well as the width and the length. It seems like here you need to find the area first and then the width and the length, but I am finding the width first because that's what comes out of that parabola. All right. Once I know the width, I can go back here. I can say the length of W max It has to equal 890 minus 2 times 222.5. And it turns out that this is 445 feet. The maximum area, I'm just going to take those two things and multiply them together, right? Width times length. I know the width, 222.5 times 445, and that gives me this answer. I have it over here, 99012.5 feet squared. That would be the answer. And you can see I'm writing over this little piece of white on my screen here. Of course, what you know is I graph this, right? I did everything algebraically. I think that's the thing that most students have trouble with when they work on this problem, is solving algebraically. How do I get that univariate equation in part B here? How do I get this univariate equation, this one right here, to be able to solve for the vertex? Okay. Any other problem where you're working with fences or pens or what have you, you're going for that univariate expression to be able to solve for a vertex. Okay, let's look at the graph here. Let's see what the graph shows us. What I graphed was this function here, and I located the vertex. Okay, so you can see here's the function, -2, I put an x squared, not a w, I put an x squared, -2 x squared plus 890x. All right, and there's the vertex. I put in the value that I solved for algebraically in here, and you can see that that's where the peak of that vertex is. So a cute little problem that I see students struggle with. Hopefully that gives you some leg up on solving min-max problems or intersection problems to be able to get through your word problems. The next portion of this lesson has to do with regression with quadratics. And I had covered regression with linear models in a prior lesson, so you can go check that out. There were some fundamental things about regression that I introduced in that lesson that is true for all functions, regardless if it's linear, quadratic, power, any function in there that's going to be true, such as always graph the data. Always graph the data. You're going to notice at that point, what's the shape of that data? What's the shape of that data looks like? As we move forward to quadratics, we're going to still graph the data. I have this graph here of this data, and you can see that it's not linear. This is not a linear. So that's why I'm saying linear versus non-linear should be identified immediately when you look at that graph. And that's why we graph. The first step, always graph your data, all right? Don't do any analysis on your data until you graph your data. Always graph your data. And that should tell you, what is that relationship? We can see clearly this is nonlinear. And I would say it's roughly quadratic. It's not perfectly quadratic. You can see that there's data points in here that are off the main sort of trend, but it's roughly quadratic. And when we're doing this, we're going to assume the model of this form, right? An ax squared plus bx plus c, our general form of the quadratic. The first method that we used when we covered this with linear models was a line of best fit. And I do believe in, like, if you do homework for me, that gives you this data and you need to choose a point and choose another point, and then it'll fit a line, the best fit line to that. It doesn't need to be perfect. And that's fine. I think that's fine. But for me, I like exact answers as a scientist, and applying this mathematical models in real situations. I want a real equation. I don't want some guesstimate. And we're going to let the technology work on that, right? So here's the line of best fit in here. Actually, this is the line that the computer said was the best fit. But what we're going to do is let technology use statistical techniques to mathematically minimize any residuals or errors. And that's a stats class, right? I have you all looking at the output. Okay, so you're going to input your data into the analysis program, whether you're using Desmos or Excel or any other one that I'm fine with, but I'm teaching Desmos and Excel. And fit a quadratic, I copied and pasted this, fit a quadratic regression model. Quadratic regression model, all right? So if you're in Desmos, you need to tell it. I suppose there's a drop down, but I prefer for you to tell it what that model is. So we'll say y goes as ax squared plus bx plus c, our general form, all right? In Excel, it doesn't have a quadratics option. What you have to choose is a polynomial, and then you need to tell it it's an order 2 polynomial. And we know that. It's an order 2. That's what the order is what's the highest power of x. It's 2 in this situation. Okay, so you're familiar with how to do regressions. There's a few things that come with regressions that I might want to mention is remember that we talked about how well models fit the data. You will get an R squared with the quadratic regression model as well, and you'd be expected to know what that means and interpret it. So I grabbed a few examples here that I see students struggle with. The first one here is the fuel consumption. I don't think this is terrible of a problem. They already give you the regression model here. I see the equation, the regression model here. It says the table shows fuel consumption of all vehicles in the U.S. for the years since 1990, all right? So we're going to say that this is 1990, this is 1993, this is 1996, etc. So we're just going to put in the years since 1990 in there. And then let this fuel be the consumption in billions. So this isn't 130.8 gallons. It's 130.8 billion gallons. All right, so watch that billion in there. A quadratic model for the data is blah, blah, blah. So they give us that. Use a scatter plot to decide whether the quadratic model fits the data well. Okay, so I went ahead and I plotted this data. Where did I plot this data? I do believe this is the plot for the data. There's the plot for the data. And you can see overall that this is data is, I mean, you could fit a quadratic to it. You could really try to fit a quadratic to it. I think it would, it's this first data point is kind of off. I think the rest are a little bit more parabolic. This in here looks more linear, but the two ends, this one going down, this one going down is what makes it parabolic. I would say I would not use a linear function because I see this peak going on. All right, so we see that the quadratic model fits the data well. It says estimate the fuel consumption in 2009. Okay, so what I see students have trouble with on this problem is they're like, okay, fuel, I'm going to plug in a value and just plug it into my calculator and I can do that stuff, right? Which I agree. I think this is, the right thing to do, and then plus the 127.598 on the end. I think that's the right thing to do is to plug in a value, but what I see students struggle with is they want to put 2009 in there, which is not the right thing to do. Remember, we want years since 1990. So if I am at 2009, that's 19 years since 1990. All right. So when I evaluate this, I want to put the value 19 into that equation, and that will give me the right number. This turns out to be 174 billion gallons of gas. Of fuel. All right, so that's part B. Part C here says use the model to predict the year in which U.S. fuel consumption will peak. Oh, so words mean things. Peak. Peak means vertex. Okay, so we're going to find the vertex. We're going to find the time where it reaches a maximum value, and so I'm going to need a negative b over 2a. Negative b over 2a, I'll get negative 4.620 divided by 2 times negative 0.114. Get the ones in there, and when you solve this value, you get 20 point something. 20.263 years. Okay, so 20 point something. And I have a feeling students try to put that in as the answer, and it's not the wrong calculation, but it is the wrong answer in the sense that it wants the year. So remember that this is 20 years since the original date. So we're going to have to put 1990 plus 20, so that's going to be 2010. So that's the answer that they want for this problem is 2010. Don't put in that 20 in there, put in 1990 plus whatever your answer is. So that's where I see students having trouble with this problem. Here's the fit here. I'll bring this forward. There's the fit according to the homework problem that I pulled this from. I actually put this into Desmos. I put the data into Desmos for myself, and you can see the equation there. I'll move it over so that you can see the equation a little bit better here. Negative 0.1136, so we can see it was rounded, and it's a pretty good model. It's not exactly, I think that's why I did this, was to look at the model. The r squared here, r squared is 0.9655, so that it's pretty good. I would say that's a pretty good. It's not a perfect fit, but we already knew that looking at the data. We had a couple of data points that were a little bit, this being linear in here, but then it went back down. What I did was I put a couple of points in here. I evaluated it at 19. When it's 19, there's the value. When it's 19 years after 1990, and then the number I calculated for the vertex, you can see that the vertex is right there, 20.263. Corresponds to that vertex value. Okay. So hopefully that helps you with that problem, remembering years after 1990. I think that's the biggest issue on that problem. This one here is kind of interesting. The hockey arena, hockey tickets. A hockey arena seats 1,600 people. The cost of a ticket is $10. At this price, every ticket is sold. To obtain more revenue, so there's a demand. There's absolutely a demand. It's selling out. So they think, let's raise the price. To obtain more revenue, the arena management plans to increase the ticket price. A survey was conducted to estimate the potential revenue for different ticket prices, and the shown resulting data can be modeled by a quadratic regression function. All right, so this is the data that they collected. All right, so $10 a ticket. This must be 16,000. Sorry, this is 16,000, not 1,600. Okay, so 16,000. If the ticket price is 15, then they estimate that 19,500 people would show up, and so on, right? That's how their ticket sales that they predict. So it says determine the regression function that models this data and determine the ticket price that would maximize. So I'm going to see words mean things. This means find the vertex of it. So I need to find the regression function, and once I find the regression function, I'm going to find the vertex. Okay. So run this through Desmos or Excel. That's the easiest thing to do here. Not going to do any algebra yet on it. When I run this through Excel, this was my output. I can see the output here. So I'm going to write this equation down. They tell me that the potential revenue as a result of the number of tickets sold, so I'll say revenue and tickets sold, is negative 91x squared plus 3125x minus 6340. That's the equation that came from my data, okay? I just plugged it into Desmos, and that the Desmos fit that parabola to it, okay? So that's going to be my answer for the first part here. What's the regression equation? There it is, done. And I even put it in proper function form. The second part here says determine the ticket price that would maximize the revenue. Okay, so maximizing the revenue, we're going to find the vertex. And now that we have the form of our equation here, the regression equation, we're going to remember that in order to find the maximum value of tickets that would result in the maximum revenue, we're going to do negative b over 2a. So I'm going to go negative 3125 divided by 2 times negative 1. That gives me a positive value. And when I run this through my calculator, let me check the answer here first. It gives me $17.17. 1717. That's the answer I get when I divide those. Okay, so it's in here somewhere. They didn't collect that data, but it's in here somewhere. And if we look at that graph again, let me bring this graph up again. This is the second one. Okay, so let me bring this to the front. You can see that I put that value in there. This is the original output that I had, but then I put in x equals 17.17, and you can see x equals 17.17 is the vertex of that parabola right there. Okay, so I am confident that $17.17 is the answer to that problem. So I'm getting my graph to correspond to my algebra. And a key thing I see in here is that, they're having you do a couple of different skills. They're having you do a regression equation. Can you just have a computer calculate the regression equation? And once you get that regression equation, can you interpret it in order to find different values from it? In this case, they wanted the vertex of that parabola. There may be other things that they ask you to solve for. It could be like, what's the revenue when you sell 50 tickets, right? They may ask you to evaluate the function. They may ask you to find some intercepts. Depending on the problem, you'll have to remember your different strategies for working with quadratic functions in order to solve for different values. So hopefully that helped you with this lesson.